Okay, welcome back to an exam walkthrough from light and polarization. In this video, we'll be looking at a question from light and physics. So this is from 2025 October, Unit 2, and question number 14. So here it says, a student used a semicircular glass block to investigate the refraction of light. He directed a ray of light onto the glass block as shown. And then we see this light that's going straight like this, right? And it says state why a ray of light does not refract as it enters the glass block. So the answer here will be that the incident ray of light enters along the normal. So you have to remember, whenever the light enters along the direction of the normal, or when it does that, there's going to be no refraction happening. It's just going to pass straight through. Okay, so the reason why this happens is, now notice this light, it enters from a less dense medium to a more dense medium. And this light, which is incident, enters along the normal. These straight lines are what we call as the wave fronts. Wave fronts. And this distance between two wave fronts is the lambda. And notice when it goes from less dense to more dense, the lambda value decreases. Remember, when we have refraction, we know the formula, velocity is equals to f lambda. Two things change whenever refraction happens. The velocity is going to change, and next the wavelength will change. But the frequency remains the same. Now another thing that happens in refraction is that you have a change in direction. Change in direction. Okay, and these two things, when you consider them, that's when you can tell if something is refracting or not. Now, in this case, you can see that the lambda value is decreasing. So the speed is also going to decrease of the light ray that's entering. But there is no change in direction. And the reason for this is that the entire wavefront enters the medium. So let's say this is medium A and this is medium B. So it enters the medium B, the entire wavefront enters the medium B at the same time. So the speed of the entire wavefront decreases at the same time. Okay? And that is why, since their speed decreases at the same time, so their direction does not change. Okay? Refraction happens because when you have light entering like this, okay, you have light entering like this, you can notice that this part of the wavefront is going to be, let's say B is more dense, right? B is more dense. Okay, I think we've already said that as well. Yeah, it's more dense. Okay, so this is traveling at a slower velocity, and this part of the wavefront is traveling at a faster velocity. Because of this, there happens to be a change in direction. Okay, but here that doesn't happen because the entire wavefront enters at the same time. So I wanted to emphasize this. I could have just written it down, but this is an important point, so keep this in mind. This has come up before as well. Okay, coming back to the question, here we have, remember, air. I don't think they have specified it. And here we have the glass block. Now they say that the glass has a refractive index of 1.5. The ray of light is refracted at the curved surface of the block. Calculate the angle of refraction. So we can use the formula N1 sine theta 1 is equals to N2 sine theta 2. So we can say here N2 is going to be, this is all about air and this is all about things happening in glass. Okay, now we're going to say that in the glass the refractive index is 1.5, the angle is sine, what was that, 35, sine 35. And then we have air, refractive index as 1 and sine theta 2. Then you solve for sine theta and you're going to get 54.5 degrees as your answer. Now before we go to the next question, remember when we go from, here's the example, when we go from, this is less dense, this is more dense, and this is less dense. When we go from less dense to more dense medium, the refracted ray will bend towards the normal. When we go from more dense to less dense, it will bend away from the normal. And keep in mind, notice here, one sec. Okay, so here This is going to be the angle of incidence, and this is going to be the angle of refraction. Okay, and here this is going to be the angle of refraction, and this is the angle of incidence. Okay, you can also say the other way around for this one as well. You can say this is the angle of incidence and this is the angle of refraction. It just depends where the light is going to hit. Okay, so in our case above, we can see that this is angle 35 degrees, this is angle of incidence, and then the light ray will bend away from the normal because we're going from glass to air, so we're going from more dense to less dense. And then this angle here is going to be the angle of refraction, 54.5 degrees. Okay, so the same thing here as well, angle of incidence. Okay, and then you have this angle of refraction, how much it bends away from the normal, right? That's the answer to this question. So here's the answer to this part of the question. Now we'll move on to the final part of this question. So here's the final part. It's a bit of a tricky question at the end. The student moved the glass block so that the ray of light was incident on the curved surface at the critical angle C as shown below, and have to determine the distance x. So this is a critical angle, so we can say n1 sine theta 1 is equals to n2 sine theta 2. And then we know at critical angle, if we take an example like this, give me 1 second. So at the critical angle, our incident angle is just equal to the critical angle, and then our theta 2, which is this one, is going to be 90. So we have n1 sine theta c is equals to 1 times sine 90, and sine 90 is just 1. You can plug that in the calculator, and then we get sine theta c is equals to 1 over 1.5. And when you solve that, you should get 41.8 degrees. So this angle here is 41.8 degrees. Not degrees Celsius, just degrees. Okay. And then they have given you the radius of the glass block. Now, one very important thing you should remember is that the radius is the distance from the center, which in this example above is going to be O. So from the center O to the circumference. So notice this is the radius R, this is the radius R, this is also the radius R because it's the distance from the center to the circumference. This is the circumference right over here. This entire thing is a circumference. This is also the radius, this is also the radius. Okay, what is not the radius is this. You can't say this is the radius because it's not from the center. Okay, so here we can see that, 1 second, okay, that this is the center. Okay, if we draw the full circle, this is going to be the center. This over here is the radius R, this is also the radius R, and this is also the radius R. I hope that makes sense. Okay, the reason it appears a little weird, notice it appears a little different, is because they have told us this is not to scale. Okay, they've given this just for the theory part, just for us to be able to draw on it and write it. It's not to scale, it's not perfect. Okay, so what I can say here is I know this distance is going to be 45 millimeter, and I know this entire thing is going to be 45 millimeter. I think it's getting a bit complicated. Let me just move some things out of it. Okay, and then now I'm going to I need to find this distance right over here. Okay, so we can find the distance quite easily because we also know this is 45, right? So we can just do that. We have the triangle right over here. This is 45. This is x. Let's call it y, and this is 41.8. So then we get this, and then we can find y. So our y is going to be 29.99 millimeter. Okay, so this is our y will be 29.99, and then we can just add it to 45 to get x. So plus 45, and we get 75 millimeter as our final answer. So here is the mark scheme. You can go through it and then we'll end the video.